This video will cover typical approaches for representing channels in a 2D model. Terrain data is the most important data set used for representing hydraulic models because it has the largest impact on model results. Terrain data used for hydraulic models should represent important hydraulic controls such as channels, roadways, and levees. LiDAR data, provided in point or raster file types, is the most common type of data used to represent digital terrain surfaces. However, LiDAR does not typically provide data below water, so additional data is usually required to create a more complete topographic representation of a project area. There are 4 common approaches for representing the channel in the terrain surface, including a complete bathymetric survey, interpolated cross-sections, using a representative channel section, and approximating a channel. Additional survey data will be required to sufficiently represent the channel below the water surface for most hydraulic models. When working with multiple terrain data sets, always verify that vertical datums are consistent before merging. Obtaining a thorough bathymetric survey is the best approach for representing the channel. Multi-beam survey data or dense single-beam cross-sections are typical methods for obtaining a complete survey of the channel. The survey data of the channel can then be merged with the overbank LiDAR. This approach provides the most complete representation of the project area. When merging any type of channel and overbank data, review how the 2 datasets are triangulated together and add break lines as needed to avoid artificially high areas within the channel area. A complete bathymetric survey of the channel is not always feasible due to access, budget, or timing constraints. Another approach for representing the channel is with sparse cross-sections. This is similar to the type of data that is typically collected for 1D hydraulic model studies. While this type of data does not provide a complete representation of the channel, it does provide enough data that can be used to interpolate between each cross-section to provide a reasonable representation of the channel terrain. Adding break lines is a common approach for interpolating data between each cross-section. Multiple CAD and GIS software applications have various methods for interpolating data along curved alignments like channels. It is common for channel data to be collected in the vicinity of a bridge, but not along the entire channel within the model domain. In this case, one option to filling in the rest of the channel is to create an averaged or typical channel section from the available channel survey data. The typical section is intended to represent the conveyance area of the channel not represented in the LiDAR and outside of the area where survey data exists. Representing the approximate conveyance of the channel in the terrain data allows the model to more accurately determine the distribution of flow across the floodplain. This is especially important when significant flow is leaving the channel and when split flow exists. Without the approximated channel, the split flow values would be less representative of actual conditions. This approach does not provide detailed local hydraulic results where the channel terrain is approximated. However, for bridge projects, detailed local hydraulics within the channel away from the bridge of interest are not necessary. The last approach is to create an approximate channel throughout the entire domain. This approach is not recommended for model areas of focus such as at bridges. However, it is a reasonable approach for coarse models or for channels away from the area of focus. An approximate channel should attempt to represent the conveyance of the channel below the water surface of the LiDAR, similar to the previous example. A common method for developing approximate channel dimensions is to determine or estimate the discharge in the channel during the LiDAR flight. An approximate channel can then be developed based on the average slope of the channel and the discharge. An approximate channel can then be developed using methods within SMS, CAD, or GIS applications and merged with the rest of the topographic data. The approximated channel can be a V-notch or trapezoidal in shape. SMS has several tools and functions that may be helpful when developing approximate channels. Feature stamping and cross-section interpolation are 2 options that may be useful. Resources explaining both of these are available in the SMS Learning Center. In addition, SMS has the ability to blend and transform lines. This functionality can help streamline the creation of an approximate channel, especially when channel or water's edge break lines are provided with the LiDAR data or other survey data. The blend function creates a line between two selected lines. For instance, if two channel edge breaklines are selected, the blend tool can create an approximate center line. By repeating this process, additional lines can be created that represent toe of channel slopes. The blend function will preserve elevation data of the lines. The transform function allows the user to move the line around in space in the X, Y, and Z direction. This function can be used with the blend function to adjust lines to the desired location and elevation. These functions and tools can be used in conjunction with other software or processes within SMS to help develop approximate channels. Representing the channel bathymetry is an important step in creating a complete representation of the terrain for use in a 2D model. It is common to have to represent the channel with a combination of data types, including surveyed and approximated channel data, then merge this data with LiDAR.